Okay, when doing a problem like this, you always start with your conservation of momentum statement. When you're doing this, you would need to recognize that this is conservation of angular momentum, and you would need to avoid instincts of seeing an MV here and treating this as a conservation of linear momentum problem. So we're going to say that the initial momentum of both the ball and the rod, that's what the subscripts B and R are representing, are equal to the angular momentum of the ball and the rod together after the collision, if in fact angular momentum is conserved. We know that the angular momentum of the rod is initially 0, so we ignore it, and we can say that the angular momentum of the ball, which we're going to treat as a particle, is mvr perpendicular. That's equal to I omega final for the ball and I omega final for the rod, where the omega finals of the ball and the rod have to be the same number if the collision is inelastic and they hit and stick together. So therefore, I'm going to remove the subscripts and just call it omega final, the final angular speed or angular velocity of the system. And then I have to, once I factor that out, I have the sum of their moments of inertia. I'm going to treat the ball as a point mass, and I'm going to treat the rod as a bar pivoted about its end with an equation that would have to be given to you in the problem, 1/3 ml squared. Plugging those numbers in, I may have made a mistake here, so check my results. So this is half of 6, which is 3 times 1. 3 divided by the sum of the two moments of inertia gave me around 2.6 meters, sorry, not meters per second, but radians per second. I only had one sig fig over here, so I'd probably need to round that up to 3 if I wanted to watch my significant figure rules. Did anybody else get this numerically? Okay, are there questions on that?